This lesson is about solving inequalities. So the previous 4 lessons that you saw were all about solving equations. Equations have equal signs, like in these 3 problems. So hopefully by now you're pretty comfortable solving equations, you're familiar with solving equations, and now we're going to start solving inequalities, which are different. The process will be the same for solving these inequalities, but it won't have equal signs. All right, so go ahead and start. We're on page 103. Under the introduction, there are 3 problems for you to solve. These are equations, so you should be able to solve them yourself. Go ahead and take a moment to solve each of those 3 equations, and you can unpause this video when you're ready to see the answers. All right, are you guys ready to see the answers to the 3 equations? All right, here we go. Here's the answers that I got. All right, so the first one was a one-step equation. I divided both sides by 8, and I got x equals -4. Because -32 divided by 8 is -4. On number 2, I have x divided by 4. To cancel that, I multiplied both sides by 4 to cancel the denominator, and I got x equals 12 times 4, which is 48. Number 3 is a two-step equation. First, I added 7 to both sides to cancel the -7. I got 5x equals -5. Then I divided both sides by 5. I got x equals -1 as my answer. All right, so that's just a quick little review of solving equations. But in this lesson, we'll actually be solving inequalities. Well, what is an inequality? An inequality means 2 expressions that are not equal. 2 expressions that are not equal. Equations have expressions that are equal to each other. Expressions means any combination of numbers, variables, and operations. So 8x, or 8 times x, is an expression, and that is equal to -32. In number 3, 5 times x minus 7, that is an expression that is equal to -12. So equations have 2 expressions that are equal to each other. An inequality has 2 expressions that are not necessarily equal to each other. That's the main difference. For inequalities, we're going to have one expression is going to be larger than the other. And to show that, we have these 4 inequality symbols, which should look familiar to you. These 2 inequality symbols show one side being greater than or less than the other. This first one is called the less than symbol because it shows that the left side is less than the right side. So that opening always goes to the larger side. So that means that the right side is more than the left side. This next symbol is another inequality symbol. This one shows that the left side is more than the right side. So I would say that this is greater than the right side. So this is the greater than symbol. These 2 symbols are the same. We see a less than symbol and a greater than symbol, but they have one extra piece underneath. This extra piece underneath is one of the 2 lines of an equal sign. So it's kind of like we took a less than symbol and an equal sign, put them together to get this symbol. This is called less than or equal to. So in that case, the 2 sides could be equal, or one side is more than the other. So we say that's less than or equal to. Similarly, this symbol is greater than or equal to. And we'll see those symbols in action as we solve some of these problems. So we're basically going to take these equations and do the same things we've been doing to solve an equation, but instead of an equal sign, we'll have one of these four symbols instead. But we're not there yet. Let's talk a little bit more about what these symbols mean. So in this part, we're going to write an inequality to represent each situation. So here's a situation. Jose wants to earn at least 80% on his test. At least is the key phrase there. At least 80%. That tells me that Jose would be fine with getting 85%. He'd be fine with getting 90%. He's happy to get a grade better than 80%, but he does not want a grade that's going to be lower than 80%. He would not be happy with a 75 or a 60%. That would not be good enough. He wants at least 80%. So I'm going to use J for my variable just to stand for Jose. So Jose wants at least 80%. So he wants more than 80%, but it looks like he would be okay with 80% itself. So I'm going to say greater than or equal to. He wants his grade to be 80% would be okay. More than 80% is good too. So greater than or equal to 80%. Carrie wants at most 30 problems on her math homework. And this one is at most 30 problems on her math homework. So think about at most 30 problems. So would she be happy with 34 problems? Would she be happy with 25 problems? Would she be happy with 30 problems? If she wants at most 30 problems, it sounds like 25 problems is fine, 26, 27, 28, 29, even 30 problems would be okay with her. But she does not want to have 31 problems or 32 or more than that. So I'm going to say that Carrie, she wants to have less than or equal to 30 problems. 30 is okay, anything less than 30 is okay, but anything more than 30 would be too much. Carla can carry no more than 5 books in her backpack. No more than 5 books. So she can carry 1 book, 2 books, 3 books, 4 books, and 5 books. But 6 books would be too heavy for her. So Carla can carry less than or equal to 5 books. I put or equal to because 5 books is okay, but more than 5 books is not okay. Leo wants to earn no less than $100 at his job this week. Maybe he's saving money for something. No less than $100. So Leo wants greater than or equal to 100. Samantha is not old enough to drive. Not old enough to drive. It's a little bit vague. We don't know if this is talking about a learner's permit or a driver's license. I'm going to assume it's a driver's license, which you can get when you are 16. So I'm going to assume that this tells me that Samantha is not yet 16. Maybe she's 15. Maybe she's 15 and a half. Maybe she's still a baby. I don't know. We don't know how old she is, but we do know she's not old enough to drive. So I'm going to say that Samantha's age is less than 16. She could be, maybe she's turning 16 tomorrow. So she could be 15 and 363 days old. We don't know, but she's definitely not 16 or older. She's less than 16. On the other hand, Eric is old enough to vote. Voting age in the United States is 18 years old. So that tells me, I don't know how old Eric is. Maybe he's exactly 18. Maybe he's 25. Maybe he's 72. I don't know. All I know is he's old enough to vote. So in order to represent all those possible ages, I'm going to say that Eric is greater than or maybe equal to 18. He could be 18, he could be older. He's definitely not 17. He's definitely not 16. He's definitely not 2. He's got to be 18 or older to vote. All right, we can also represent, so this is kind of a shortcut. Instead of listing out a bunch of numbers, like Eric's age, instead of listing out a bunch of numbers for Eric's possible age, I could just write down this inequality, and that kind of shows me all the possible ages that Eric could be. Another way of showing all of these possible answers is by graphing on a number line. So I'm going to start with this inequality. A is less than -2. Well, A could be many things. A could be -3. A could be -10. A could be -100. A cannot be 0. A cannot be 5. A cannot be -1. A cannot be -2. So there's a lot of things that A could be. There's a lot of things that A cannot be. So I'm going to represent that with a number line. Now, the important number here is -2. That's where things kind of change. So on my number line, I want to make sure that this number line includes -2. So I'm actually going to start at 0 and count backwards. -1, -2, -3, -4, -5. This can be +1. I just want to make sure that -2 is somewhere in my number line. And I'm going to shade in all the numbers that are less than -2. So numbers less than -2 could include -3, could include -4, -5. What about -3.5? That number's less than 2. What about -2.5? That number is less than 2. What about -2.1? It'd be like really close to -2, but not quite. That would be less than 2. And if I keep going with thinking of ideas, I'm going to be filling in all of these dots, all between, or all on the left of -2. So why don't I just save myself some time and shade in everything that's less than -2? So I'm going to just shade everything less than -2 to show that everything to the left of -2 and even beyond this number line, if this number line kept going, everything to the left of -2 is part of my possible answers for A. But where do I stop on the right-hand side? I know -2 is my important number. I want to count all of the numbers going up to -2, but not -2 itself. How do I do that? Well, I can show that with what's called an open circle. I draw a circle at -2 that shows that that's my important number, and I'm going to leave it open, meaning I'm not shading it in. That's to imply that -2 is not actually part of my answer. This is just kind of the boundary point of where my answer ends. That's different from this problem. C is greater than or equal to 3. All right, so I'm going to make a number line here. I want to make sure 3 is part of my number line. So I'm going to start 0, 1, 2, 3, 4, 5, 6. I can start from whatever number I want to. I started from 0 just because 3 is a small number. I just want to make sure that my important number is on my number line somewhere. All right, C is greater than or equal to 3. So 4 would be a number that's greater than or equal to 3. 5, 6, 7, etc. Also 3.5 is more than 3. 3.1. And because it's greater than or equal to 3, 3 could also be part of my number. But I do not want to include 0, 1, or 2. I don't want to include 2.5. I don't want to include 2.999999. I only want to go from 3 beyond. So for this one, I'm going to, again, shade all of those possible numbers that could be part of that inequality. And the circle that I'm going to draw this time, I'm going to draw another circle at 3, but this time I'm going to fill it in. That's called a closed circle. This implies that 3 is part of my answer as well. And that's because of the or equal to part. So when do we use an open circle? When do we use a closed circle? An open circle is when you have a less than sign or a greater than sign, but no or equal to part. A closed circle is for greater than or equal to, or could be less than or equal to. So if it has that or equal to part, you want to draw a closed circle to imply that that is part of our answer. All right, so this is how we're going to graph some of these inequalities. Let's turn the page to page 104. And just as a guideline, if I was to graph x is less than 3 on a number line, what do? I'm going to make a blank circle at blank and draw a line to the blank. So for this blank, I want to write an open or closed. In this case, because it's less than, no equal to part, I would draw an open circle. And I would draw an open circle at which number? Looks like I'm going to draw an open circle at 3. That's my important number here. And I'm going to draw a line to which side of 3? Well, if I'm graphing x is less than 3, I want to graph everything that's less than 3. So that includes number 2, number 1, 0, -1, so all the numbers to the left side of 3. So to graph x is less than 3 on a number line, I make an open circle at 3 and draw a line to the left. To graph 15 is less than or equal to y on a number line, I'll make what kind of circle at what number? Well, because of the or equal to part, I'm going to draw a closed circle. And I'm going to do that at the number 15. 15 is my important number. And I want to think about all the numbers that y could possibly be to make this inequality true. Well, 15 is less than or equal to what numbers? I know 15 is less than 16, it's less than 17, it's less than 20, it's less than 30. So all the numbers that I'm naming would be to the right of 15 on the number line. So the numbers that I would want to shade are to the right. There's also a possibility of having an overlapping inequality. Let's take a look at that. In this case, we're going to graph the following situation. X is greater than -3 and at the same time it's less than 0. So I want to set up my number line. I want to make sure to include these two important numbers, -3 and 0. So maybe I'll start at -4 and count up to -3, -2, -1, 0, 1, 2. That way I have my -3 and 0 definitely in my number line. So I want to think about all the numbers that are greater than -3 and also at the same time less than 0. So -2 is greater than -3 and less than 0. -1 is greater than -3 and less than 0. How about -1.5? How about -1/2? How about -2.5? So it looks like all these numbers that are between -3 and 0. Okay, so I want to shade all the numbers in between -3 and 0. What types of circles should I put at -3 and 0? Should I put open or closed? Well, because this only says greater than, not greater than or equal to, and this says less than, not less than or equal to, I'm going to put, for the greater than, I'll put an open circle. For the less than, I'll put an open circle at 0, and I'll shade all those numbers in between. This is a special type of inequality. It is called a compound inequality. There's two ways that I could write this inequality. I could write it as two separate inequalities. I could translate this explanation into symbols. I could say that x is, actually I'm going to start with less than, or no, I'll start with greater than -3, and x is less than 0. So I could list it as two different inequalities with an and in between to show that both are happening at the same time. I could also write it the following way. Because I'm talking about all these numbers in between -3 and 0, I could write this compound inequality the following way. I could say -3 is less than x is less than 0. Oops. Sorry, my screensaver went on. X is -3 is less than x is less than 0. This shows that x is between those two numbers. So either way you want to write it, they're both correct. And this brings me to the most important part here, solving inequalities. This is what we're going to spend the most time on, actually solving things that look like equations, but instead of an equal sign, they have an inequality symbol. So keep in mind, solving an inequality is similar to solving an equation. We're going to use the same kind of steps. And typically when we solve an inequality, we're also going to graph our solution when we're done. So let's start with this first problem. 5 is less than 3z minus 7. If I imagine that this was an equal sign and I'm solving an equation, my first step would be to add 7 to both sides. So I'll go ahead and do that. And instead of both sides of the equal sign, this time we have both sides of the inequality symbol. All right, so this cancels the minus 7 on the right. I end up with 5 plus 7 is 12. I'm going to bring down my less than symbol, and I still have 3z. And z is not by itself yet, so I also need to divide both sides by 3 to cancel that coefficient of 3, and I get, let's see, 12 divided by 3 is 4, is less than z. That is my solution to the inequality. 4 is less than z. Unlike an equation, I don't just get one number as my answer. Z can represent many different numbers that are greater than 4. So in order to represent all those numbers that are greater than 4, I'll graph my solution on a number line. Now I want to make sure that 4 is on my number line. So one way I could do that is just start with 4 right here in the middle, and then fill out the left hand and right hand sides accordingly. So 4 is followed by 5, 6, and 7. Before 4 is 3, 2, and 1, and that way I know for sure that 4 is on my number line. I want to think about, do I want to put an open circle or a closed circle on 4? Because there's no or equal to part, I'll do an open circle at 4. Now I want to think about what side of 4 to shade on. Well, think about what numbers could z possibly be in this inequality. 4 is less than 5. 4 is less than 6, 4 is less than 7, so it looks like I want to shade all the numbers to the right-hand side. So I'm going to go ahead and shade in those numbers on the right-hand side. And there's my solution. Let's do the next inequality. A divided by 2 plus 1 is greater than or equal to 6. I'm going to solve this just like if there was an equal sign here rather than an inequality symbol. I want to work on getting a by itself. The first thing I want to do is subtract 1 from each side. That gives me a over 2 is greater than or equal to 6 minus 1, which is 5. A divided by 2, a is not by itself. I want to cancel dividing by 2. The opposite of dividing by 2 is multiplying by 2. So I'm going to multiply both sides by 2 to cancel that denominator. I end up with a is greater than or equal to 5 times 2, which is 10. All right, so a could be any number that is greater than or equal to 10. I'm going to represent that on my number line. I want to make sure that 10 is part of my number line. I can do that in a couple ways. I could just start with 10 in the middle and fill out numbers to the left and right. I could also, if you like scaling your graph, maybe I want to start at 0 and count by 5s. 5, 10, 15, 20. That works as well. I like the method of just starting with 10 in the middle and just filling in both sides. So I'm going to go ahead and do that, but you can do whichever method you want. All right, so start in the middle with 10, 11, 12, 13 goes on the right, I'll count down on the left, 9, 8, 7. 10 is my important number. What kind of circle should I draw at 10? Well, A could be possibly equal to 10 here, so I'm going to draw a closed circle to show that 10 is part of my answer also. And A is greater than or equal to 10, so let's think about other numbers that A could be. A could be 11, that's greater than 10. A could be 12, that's greater than 10. A could be 20, that's greater than 10. So I'm thinking of numbers that are all to the right of 10 on the number line. So I'm going to shade, in this case, to the right-hand side. Here's another activity. Use the inequality 4 is less than 6 to complete each row in the table. 4 is less than 6. Okay, so we're going to be doing this to each side one by one. So add 4 to each side. If I add 4 to each side of this inequality, let's see, 4 plus 4 is 8. 6 plus 4 is 10, so I have 8 is less than 10. Now we started with something true. 4 is less than 6 is true. I think we'd all agree that 4 things are less than 6 things. Is our result still true? 8 is less than 10? Yes, 8 is less than 10. That is true. Let's keep going. If I add negative 4 to each side, okay. If I add negative 4, 4 plus negative 4 is 0. 6 plus negative 4 is 2. Do I have something true or false? 0 is less than 2. That looks true to me. Nothing is less than 2 things. So that's true. Now let's try subtracting some things. If I subtract 1 from each side, 4 minus 1 is 3. 6 minus 1 is 5. 3 is less than 5. Yep, that's true. Okay, subtract 10 from each side. 4 minus 10 would be negative 6. 6 minus 10 would be negative 4. All right, is negative 6 less than negative 4? Yes. If I think about a number line, negative 6 would be to the left of negative 4 on a number line. So that means that that number is less than negative 4. So this one is still true. All right, so far everything has been true. Great. Now let's try multiplying by some numbers. Multiply both sides by negative 3. Okay, negative 3 times 4 is negative 12. Negative 3 times 6 is negative 18. So now I have negative 12 is less than negative 18. Is that true or false? Well, if I think about a number line, negative 18 would be to the left of negative 12 on a number line. So actually negative 18 is the smaller number. Negative 18 is less than negative 12. So we finally have something that is false. Interesting. We'll come back to this. Let's finish up these last three. Multiply both sides by 4. 4 times 4 is 16. 6 times 4 is 24. Is 16 less than 24? Yes, it is. That is true. Now let's try dividing by a couple numbers. Divide both sides by 3. 4 divided by 3 would be 1 1/3. If I think of 4/3, that's the same as 1 1/3. 6 divided by 3 is 2. Is 1 1/3 less than 2? Yes, that is true. And last one here, divide both sides by negative 2. 4 divided by negative 2, positive divided by negative is negative, so 4 divided by negative 2 is negative 2. 6 divided by negative 2 is negative 3. True or false? Is negative 2 less than negative 3? This one is also false. Negative 3 would be to the left of negative 2 on the number line. So we have two situations where when we multiplied by negative 3 or when we divided by negative 2, we ended up with something that's false. This is important because notice that when we're solving equations, we're often adding things to both sides and we're dividing things on both sides, we're subtracting things on both sides, we're multiplying by things on both sides. So Usually, when we do that thing to both sides, that's okay. Our result is still true. We don't have to worry about that we're actually changing the value of the equation. But in these two situations, we change something crucial about the inequality symbol. Suddenly, this inequality symbol is no longer true. It is false. It's a lie. So these are two situations where if we did this one thing to both sides, we end up with an inequality symbol that's incorrect. And you'll notice that there's a similar thing that we're doing to both sides here. If we multiply both sides by -3 or divide both sides by -2. And if I gave you other examples like this, it turns out multiplying by a negative number, dividing by a negative number makes this inequality symbol wrong. In order to make this correct again, I'd have to flip this inequality symbol around. What's actually correct here would be saying -12 is greater than -18. So these are two situations where we have to do something a little bit extra when we're solving inequalities. And that comes on the next page, page 105. So which operations make the inequality false? This would be multiplying or dividing by a negative number. That makes, multiplying or dividing by a negative number. That makes our inequality symbol false. So we have to correct that. So our result is when you multiply or divide by a negative number, and only negative number. The other positive numbers don't have this problem, only negative numbers. When you multiply or divide by a negative number, switch the inequality symbol. And then you'll be back on track. And in fact, I'll show you one example of that. That's on the next page. Problem number 6 on page 106. We have -x is less than or equal to 44. -x is the same as -1 times x. So if I want to solve this for x, I would actually want to divide by -1 on each side. The negative ones cancel and I get x by itself on the left-hand side. On the right-hand side, 44 divided by -1 is -44. But because I divided by a negative number, this inequality symbol is no longer true. If I want to keep this inequality true, I'm going to have to switch the sign around. So I'm going to switch that to a greater than or equal to sign. And there's my answer, which you will then go ahead and graph on the number line. All right, that's it for solving inequalities notes. Your classwork, the pages that I need you to finish and get stamped with me, are pages 106, which we already did one problem from. So finish page 106, get that stamped. Please complete page 107, get that stamped. And then the final page is page 108. You can get that stamped as well. So pages 106, 107, and 108. Thank you very much.